Hi everybody, welcome to the next lecture on computer animation, today about optimization. My name is Gerald Schuller. So last time we saw that we can use optimization for inverse kinematics, for instance, and for that we need to find the minimum of the distance between the hand and the target. So the question is, how do we find the minimum of a function? So there is the so-called Newton iteration, which finds the zero value of a function f of x quite effectively. So here you can see how it works. So here the blue line is some function f of x, of which we would like to find the zero value. So this point down here. And depending on how this function is made, it's not so straightforward. So in this case, it's actually fairly easy because we have a so-called convex function, which means we have no local minima. And we just take some arbitrary starting point, this x0. And here you can see this is a function of just this one scalar variable. So that makes it easier to depict as a picture. So we take the starting point and compute f of x. So this is the point. And then we also can compute the derivative, the tangent df to dx. So here we have the tangent. And then we just follow this tangent where this tangent crosses the x-axis. So in effect what we do is we approximate this function here by this tangent. And then see where this approximation has the value 0. And then we repeat. At this point where the function might be 0, we compute it again. We get a different value. Again, compute the tangent, the gradient, also called the gradient in the multidimensional case, which we will soon see. And again, we follow where this function, this substitute function, this approximation function, hits the x-axis. And again, and in this way, in a few steps, we actually found a very close approximation of the true value x for which f of x becomes 0. So this is actually the formula. Here you can see the iteration. So the new point xk plus 1 equals the old point xk minus f, the function value, divided by the derivative. So remember, the derivative was dy divided by dx. So if this f can be seen as the dy, then the dy cancels, and what you have left with is the dx here, to kind of make this plausible. So f prime is just an abbreviation for the first derivative, df to dx. And we do this iteration until we reach some sort of convergence, until it's coming close enough to our desired precision. So here's actually an animated illustration of the Newton method. So it's a nice animation. Here you can see x1, we have a tangent, go to x2, have a new function value, a new tangent going down here. Then you have this function value, new tangent, get to x4. Then we have x5, and x5 is pretty much done. Right, so that works nicely. So this nicely animated example actually can be found in this Wikipedia page. But now we want to find an extremum, or more precisely a minimum, like the distance of our hand to the target. So we are not really interested in the zero of the function, but in the zero of the first derivative, right? Because if we have a minimum, then this first derivative has the value 0. Otherwise, it would not be a minimum. Observe that this also happens if we have a maximum. So this iteration now can find either a minimum or a maximum. So in this case, we just have to replace the function for which we want to find the 0 by the derivative of this function. And then this update becomes like this. So we have the first derivative divided by the second derivative here. So this leads us to this update step. And here we can see here the steps. The update steps is just the difference between xk plus 1 minus xk. And for a minimum, we need to have that the second derivative is larger than 0. So this is also a good test if what we found is actually a minimum and not a maximum. So we now extend it to the multidimensional functions f of x, boldface x. So here this boldface x is now multidimensional, and basically meaning either a vector or a matrix. So this vector x here contains many dimensions or many components, x1 to xn. So these could be, for instance, our angles of our arm with a hand, right? So the angles would be inside of this vector. So then we have our f of x. X is multidimensional, and then the derivative becomes the gradient vector, right? So here nabla f of x, this is the first derivative. The gradient is simply the function derived with respect to each of its unknowns, right? This gives us a vector as big as the number of unknowns or components that we have in the vector x. Similar for the second derivative, but now we have also combinations of those different unknowns. So here in the first row we have the first derivative to x1, and then the second derivative to the vector of all the other unknowns. Here twice x1 until x1 xn. And similar for each of the other rows. So here we have first derivative to xn and then to x1 up to xn. So this gives us a matrix of dimension n by n. And this is called the Hessian matrix. And since the order of the derivatives doesn't matter for the usual functions which we consider here, so d square f to dx1 dxn is the same as d square f to dxn to dx1, so those are identical. That means this matrix is symmetric around the diagonal. So here if we look at the diagonal, all the symmetric entries are identical. Yeah, so this becomes important later. So this can be used to now extend our Newton iteration from the one-dimensional case to the multidimensional case. So we replace the first derivative by the gradient and the second derivative by the inverse of the Hessian matrix. And now notice that here we cannot use this notation, but we have to multiply the inverse from the left-hand side because matrix multiplications are not commutative. Right? It makes a difference if we multiply from the left or the right. Here we can only multiply it from the left because the gradient is a column vector. And for a minimum, this h of f must be positive definite, which means all eigenvalues are positive. Yeah, in our previous example for inverse kinematics, the angles alpha are the x, right, this vector x, and our function optim kinematic is the function f. So this was our error function. Note that this way all components of our multidimensional vector x, for instance our alphas, can be changed simultaneously. Right here, this new x usually has all the entries, all the unknowns changed simultaneously. So the problem here, in principle, we have a very well working solution, but the problem is the calculation of the Hessian matrix. This can be very complex with large numbers of unknowns, and also we need an inverse. So this is even more true since it must be recalculated for each iteration step. So if you have many iterations, this becomes very slow. So the new approach is we try to simplify the calculation of the Hessian matrix and its inverse by making simplifying assumptions about the Hessian matrix. So there are several possibilities for these simplifying assumptions. One is the assumption that the Hessian matrix has a diagonal form. So this is really simple, right? We just assume that this matrix is basically all 0 except for constants along the diagonals. So we only have non-zero constant entries along the main diagonal of the matrix. So this is really easy to compute the product with this matrix, and also very easy to compute the inverse of this matrix. Yeah, and that leads us to the second set of our slides. So here we have again our Newton method, the multidimensional Newton method that we just saw. And the simplification now leads us to the so-called steepest descent method, or gradient descent. So here we have the simplifying assumption for the Hessian matrix that it's just a diagonal matrix. So here you can see this assumption, Hessian matrix of xk. This matrix is 1 over alpha times identity matrix. So here we just have a fixed value, and this appears on the diagonal of this matrix by multiplying with it. And that also means the inverse here is simply alpha times identity. Well, and that's also why I chose 1 over alpha here, because you really want to deal with the inverse, which is then just alpha times I. Right? So alpha is now a new parameter for the minimization of f. So this alpha should be close to the real Hessian matrix inverse if possible. But this only works reasonably if the Hessian is close to the diagonal form. So if the real inverse is actually close to this simplification. And that's by no means guaranteed. It's just a simplification which really simplifies our computation first, right? We don't really know if this is true because it depends on the f. Yeah, but in any case, it's attractive because of simplicity, because then our Newton method here simplifies by just replacing hf inverse to alpha. Right? Instead of having an inverse matrix multiplication, we just have a scalar alpha multiplication. So this is really convenient. Right? Then we just have the update is the old vector, or the old point xk, minus alpha times gradient of f at this position. And that's also why it's called gradient descent. We follow the gradient in the direction of the descent of the gradient. Yeah, so basically we have the reduction of the n-dimensional problem into one-dimensional problems, which are the derivatives which are with respect to the coordinate axis in the gradient, right, which are easier to solve. But note the assumption of a diagonal form for the Hessian matrix means a strong restriction of the objective function f. This works, for instance, if f is simply a sum of function of the individual unknowns. Right? But this is kind of a rare function. Usually we don't really have this form. So this f has symmetries along the coordinate axis, for instance, values along the coordinate axis, which is mostly unrealistic. Right? So here it actually would work, but it's not really realistic. So hence a new approach, the conjugate gradient method. This transforms the Hessian matrix into another coordinate system with other basis vectors, so that this Hessian matrix actually becomes a diagonal matrix. So this is actually quite an elegant trick, because this does not make assumptions on the Hessian matrix, but it transforms the Hessian matrix such that it has the desired shape. Right? So in this way we don't really change the matrix itself, we just transform it into a different coordinate system such that it has the desired shape. So, and that means that it works for many more functions and problems. And the basis vectors of the new coordinate system, dk, are the eigenvectors of the Hessian matrix. The Hessian matrix is symmetric, and that means the eigenvectors are also orthogonal to each other. So that's convenient, because that's what we need for a orthogonal coordinate system. Yeah, so basically this is what we are doing. We write h of f, the Hessian matrix, as a product of eigenvectors in these matrices. E contains the eigenvectors. So E contains the eigenvectors in the columns, E transpose in the rows. D is a diagonal matrix which contains non-zero entries only on the diagonal. And then the eigenvector decomposition enables this transform. It lets each symmetric matrix H be written in this form, E times D times E transpose. And this is exactly what we want because D has this desired diagonal shape. In this way we can also easily obtain the inverse matrix by just taking the same D and invert just this D to get the inverse matrix. Yeah, and then D contains coefficients on the diagonal. So these entries are the eigenvalues. Here I again write them as 1 over some alpha because later we will need the inverse. Yeah, so given an n by n matrix having n unknowns, we get n orthogonal eigenvectors dk in the matrix E, thus spanning a new coordinate system using those vectors. Another important property is for symmetric matrices like the Hessian, the different eigenvectors are orthogonal to each other, which means their scalar product with each other is 0. So as mentioned, this is important for obtaining a new coordinate system. So here a little insert about vector orthogonality. What does it actually mean? So here you can see the scalar product of two-dimensional vectors. Here vector 1, 2, here vector 3, 4. And the scalar product is just a multiplication of each of the entries and summing them up. So 1 times 3 plus 2 times 4 is 11. And the definition of the orthogonality is that two vectors are orthogonal if their scalar product is 0. So if this would be 0, they would be orthogonal. This applies also to higher dimensions, larger than 3. For instance, the following two vectors are 4-dimensional and orthogonal. So here you can see two vectors, v1, v2. And if you compute the vector product, you have 1 times 0 plus 0 times 1 plus 0 times 0 plus 0 times 0 is all 0. So they are orthogonal. Yeah, so then what are eigenvectors? If M is a matrix, our matrix, and E is one of its eigenvectors, then the eigenvectors are defined by this equation here. M times eigenvector E equals a scalar D times E. So it's simply the result of this multiplication is again this vector E, but scaled by the scalar, right? It doesn't change the direction, it just changes its length, or it points to the opposite direction if this is negative. So in general, a multiplication of a vector with a matrix results in a rotated and scaled vector, but for eigenvectors, no rotation takes place, only scaling, and that's why this works, right? And this scaling factor D is constant for a given matrix M. So that's what makes this so convenient. Instead of having a complex, having a computational complex operation like matrix multiplication, we have a computationally simple operation of this vector times a scalar. So it simplifies matters a lot. Yeah, here's a little Python example in IPython PyLab. So here we have a matrix, a simple matrix. First row is 1, 2, second row is 2, 1. So this is the resulting matrix, and then we can compute the eigenvectors using the function eig. And it returns the diagonal matrix D and the matrix of eigenvectors E. Right? And this is the result then. D is here this vector, so this contains only the diagonal of this matrix D. And here is the matrix E, which contains the eigenvectors in the columns. So here the first column is the first eigenvector, the second column is the second eigenvector. So maybe I can show it here in my little terminal to check it out. So let me increase the font a little bit. Yeah, so let's start IPython minus pylab. Yeah, I need to use IPython 3 because that's installed on my system. So here in the colorful prompt, you can see that we are now in the interactive mode of pylab. So now we can enter the matrix H equals matrix of 1, 2, first row, and now the second row, 2, 1. Finish up the matrix, and then H, you can see it's done. And then we can compute the eigenvectors, D, E. E equals Eig. So Eig is the function for computing the eigenvectors and eigenvalues of H. It's already done, so it's very quick. So here you can see D contains the eigenvalues and E contains the matrix of the eigenvectors. Very convenient. So we take the first eigenvector and eigenvalue. So here we can see E0, the first eigenvector, equals E, and we take the first column, so everything in the first column, that's E0, right, and the first eigenvalue is D0, D of 0. Yeah, so this is the resulting value, and then we can check it out. Now we can see that the multiplication of the eigenvector with the matrix, I should call this with the matrix, is in fact equal to the multiplication of the eigenvalue by the eigenvector. So now we can verify it. H times E0, right? So remember that H is of matrix type, so that means the star here means now a matrix multiplication. Right? Unlike the array type, if we have an array type, then we would have element-wise multiplication. So here we can see the result. That's indeed this one here. And now we do the same with a scalar. So now we can say D0 times E0. So we simply replace the matrix by, should be a times this vector. So actually this D0, right, D0 is really just this scalar, right? So doing the same, and indeed it doesn't make a difference, right? Here in this case we have the matrix, and in this case we simply have the scalar, and both give the same result. But scalar multiplication is much more easy than matrix multiplication. So that's convenient. Yeah, now we can also check out that the two eigenvectors are orthogonal to each other. So for that I also need to extract D1 equals E1. E1 equals E of now the second column with index 1. And now we compute the scalar product as E0 transpose, which will be a row vector, times E1, which is a column vector. So this is again a matrix multiplication, but since both are vectors, then this results in the scalar product. So E0 transpose times E1. And we see indeed we get the scalar 0. So in this case the scalar is of matrix type because both were of matrix type here. And a product of two matrices is again of type matrix. Yeah, so this works. So this is the requirement that we need for a new orthogonal coordinate system. So that's good. So This means we can now do a coordinate transformation. The eigenvectors now become a new coordinate system. We obtain the new coordinates by forming the scalar product of the vector from the origin to a point with the new unit basis vectors. Right, so we have the point P here, and this P, the coordinates basically are represented by a vector from the origin to this point. Right, and now we multiply this point, this vector on point, with a unit axis vector. So here we have x nu, which is one of the decays. Right, so we multiply it with it, and the result is the projection of this point, this orthogonal projection on this axis. Right, this results in the required orthogonal projection onto the basis vectors. So remember, the scalar product is of two vectors is the length of the two vectors multiplied times cosine of the angle between them. And if the length of one of the two vectors, the axis vector here, is 1, then the new vector is just the length of this vector 2p times the cosine of this angle. And this is exactly this orthogonal projection on this new axis. Right. So here would be the old axis. That would be, again, the same projection. And if we have a new axis, we just have the multiplication with a new axis vector. And the same with the y-axis and the z-axis. So we would take the same point P as a vector and multiply it with a unit length axis vector y nu. So that lets us change the coordinate system. Right. So for the 3 new coordinates, we need accordingly 3 scalar products with the 3 new basis vectors. We can collect these basis vectors in a matrix. It is identical to the matrix of the eigenvectors E. So this should be 2 to the matrix of the eigenvectors. And if P is a column vector in the old coordinates, we get the new coordinates accordingly by the matrix multiplication here. So here we have this column vector P old. Here we have the matrix of eigenvectors. Since we transpose it, now the eigenvectors are in the rows, so that each row is a scalar product of one of the basis vectors with this vector of P old. And as a result, we get 3 new entries here, new column vector, which contains the new coordinates in the new coordinate system. Yeah, so the matrix E transpose has the basis vectors along the rows as required. The inverse transformation is correspondingly P old is the inverse of this matrix times P nu. And because of the orthogonality, we also know the inverse is identical to the transpose, and that means the inverse cancels this transpose. So we just would need to take E times P nu, which we see here. Right. Yeah, so this leads us then to the transformed Newton iteration. Right. So here we have our Newton iteration that we just saw. Here we have the inverse Hessian, here we have the gradient, and here we have our E, the eigenvectors of our Hessian matrix, and here the matrix D, the diagonal matrix of the eigenvalues of our Hessian matrix. Right, so now basically we can take this iteration and transform it into the new coordinate system. Right, so the Hessian matrix and the gradient in the new coordinate system will be then this one here. So we have this xk in the old coordinate system. Then here we take the inverse Hessian and write it here in the new coordinate system, d to the minus 1. Here we have the transform from and to the new coordinate system with the E and E transpose. Here we have the gradient and transform it into the new coordinate system, into the old coordinate system I should say, because nabla D D denotes the gradient in the new coordinate system. And then we can see here this E cancels, and what's left here is simply this E times D to the minus 1 times nabla in this new coordinate system. Right, so this nabla delta here is the gradient in the direction of the eigenvectors dk at the point xk. Yeah, so here this is in the new coordinate system, and it's connected to the gradient in the old coordinate system by this coordinate transform matrix E. Yeah, so now we have the inverse of this diagonal without any assumptions about the Hessian matrix. All what's left is this transform matrix E. Right, so this is really convenient because we don't need to worry about the inverse of this matrix anymore, but we still need to have this E, right? This E depends on the Hessian matrix. Yeah, so here's another insert about matrix computation, about the inverse of a diagonal matrix. So here we take two diagonal matrices which have entries only on the diagonal. The result is simply the multiplication of each diagonal entry. So 2 times 4 is 8, 3 times 5 is 15. Here you would have the inverse, 2 times 1/2 is 1, 3 times 1/3 is 1. So here the result is identity. That means here the right matrix is the inverse of the left matrix. And in general, this is true. If you have a diagonal matrix and you want to have the inverse, you just invert each of its diagonal entries. So that's very convenient. Yeah, so as illustration, with the transformations with the E matrices, we transform the old coordinate system into the new coordinate system where the eigenvectors represent the new axis vectors. We now calculate the gradient of the Hessian matrix in the new coordinate system, right? So we need to take the derivatives with respect to the new coordinate system. The vector of the unknown x is still in the old coordinate system, so for the update of these vectors, we need its back transformation into the old coordinate system, again multiplication with E, because we're doing the updating in the old coordinate system. Yeah, so here's our update equation again. So it's very easy up to this part here, gradient times the inverse of our eigenvalues. We just need to have this transform E here, this transform matrix. Yeah, so this D contains our alphas on the diagonal, but now different alphas, right? They don't need to be the same. Yeah, the gradient is simply in the direction of the eigenvectors. So we have the df in the direction of d1, d2, and so on. Yeah, so here again we have a reduction of an n-dimensional problem to n one-dimensional problems, which are more easily to solve. Right? So here this part, d to the minus 1 times gradient, is simply n derivatives multiplied with the different alphas. Right, so this is a vector of n one-dimensional problems, and this derivative can be simply obtained numerically by shifting the x a little bit into the direction of those eigenvectors minus the old point and divide by epsilon. Right, so this is a numerical approximation of each of those derivatives. Alternatively, if you happen to have the gradient in the old coordinate system, you just need to multiply with a vector dk, with eigenvector dk. So this means here we can apply one-dimensional Newton, right? And we need no big assumption for the Hessian matrix. It also works for non-separable functions in this way, and the dk are also a more direct direction to the minimum, so it leads to much faster convergence. Yeah, so note here we have again a method which is very similar to gradient descent, only in different, more suitable coordinate system and with different factors alpha k. So this transform was key, the transform in a suitable coordinate system. Yeah, and that should be it for today. Thank you for your attention and bye bye.